All right, so let's move on to chapter 4, which is probability. This is a typical table we're going to encounter in chapter 4. I deal a lot with the conditional probability. All right, first one, let's look at a rare event rule. So if you're under a given assumption, Lowry is fair, right? The probability of a particular observed event is extremely small. Then we say this assumption is probably not correct. So that's a rare event rule. So sometimes you can use it to judge any assumptions, made associated with any particular event, whether it's true or not. Let's take a look at some fundamental definitions. First one is called definition. So definition is basically a procedure. So procedure is basically procedure is action whose outcomes result is random. And the event is any collection of outcomes of a procedures. So event is basically a collection of outcomes for any particular event. A simple event is an event that cannot be simplified even further. And sample space of a procedure is a set of all simple events. Let's take a look at examples, right? First one is procedure. So rolling a die, rolling 2 dice. That is a typical procedure. Event. For 1 die, right? Any of 1, 2, 3, 4, 5, 6. Like getting a 1, getting 2, getting 3, getting 4, getting 5, getting 6 is an event. And getting even number is an event. Getting a number which is greater than 3 is an event. For 2 dice, sum is 7, sum is bigger than 10, 1, 1, 1, 2, 2, 1, both event. That could be event 2. Let's take a look at simple event. Simple event for 1 die, getting a 1, that's a simple event. Getting 2 is a simple event, etc. For 2 dice, getting a combination of 1, 1, or getting combination of 6, 6, that is simple event. And sample space of procedure is the set of all simple events. So sample space includes all simple events which could occur in this particular procedure. And let's take a look at some important notations like P, which represent probability here. Capital letter A, B, C represent the specific events. And P, parenthesis of A, represent the probability of event A occurring. Let's learn how to define a probability using 2 different approaches. First one is called relative frequency approach. So basically observe a procedure a large number of times and count number of times that event A occurs. Then the probability of A is estimated by P, probability of A equals number of times A occurs divided by number of trials. Example, let's take an example of attack force up. So repeat the experiment 1,000 times and count how many times the attack force up. The probability of A is the ratio of number it forced up over the number of times the attack was thrown. That's a relative frequency approach. Second approach is called classical approach. So if a procedure has n simple different events that can occur that are equally likely, and there are s different ways that A could occur, then probability of A equals to number of ways A could occur over number of simple events, which is equals to S of n. Okay, let's take a look at example. And let's assume we roll the die, right? Assuming the die is not loaded, each face has the same chance of falling upside. So the probability of getting even number is equals number of ways getting even number divided by total number of options. So here we get a even face could be 3, could be 2, 4 and 6. So that's 3. Divide by total number of options, which is 6. So when you divide, then you get half. And also, that's another way of defining a probability is called subjective probability. So probability of event A occur is found based on the knowledge of relevant circumstances. So, for example, like weather forecast. So basically, you need to be an expert to estimate wisely if it will rain tomorrow or not. Okay, let's look at a roulette example. Bet on number 13 on a roulette game. What is the probability that you will lose? So on a typical roulette game, there are 38 slots, all equally likely. So use classical approach. 37 results. Use classical approach. 37 results in loss. So only one number will be the winning number. So probability of loss will be equal to 37 over 38. Next thing then, let's take a look at the law of large numbers. So law of large numbers states as a procedure is repeated again and again, the relative frequency probabilities of an event tends to approach the actual probability. So basically here, S over N approaches the actual probability of event A. An example is a death penalty example. In a Gallup poll, adults are randomly selected and asked if they are in favor or against the death penalty. The responses include 319 who are favored, 133 who are against it, and 39 that have no opinion. And based on these results, estimate the probability that a randomly selected person is in favor of the death penalty. So we get a 119, which is in favor, 133, which is against, 39, which has no opinion. So the total number of people we survey is 491. So using the law of large number, right, probability of event A, which is in favor of the death penalty, equals to amount of people who in favor of that divided by total people we surveyed, so which is equals to 319 over 491, which is equal to 0.65. Let's take a look at another example. Let's say we a couple decide to have 3 children, right? And what is the probability that exactly 2 out of 3 are boys? So basically the couple wants 2 boys and 1 girl. We're assuming that having boys or girls is equally likely. So let's use the classical approach. So options are boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. So there are 8 options here. And those outcomes who has 2 out of 3 are boys are labeled in red. So boy, boy, girl, boy, girl, girl, boy, girl, boy, boy. 3 out of 8 total options. So 8 possible outcomes, 3 corresponds to exactly 2 boys. So our probability of exactly 2 boys equals 3 over 8, which is equals to 0.375. Next thing, let's look at a complementary probability and properties. Let's take a look at an example of Thanksgiving Day. What is the probability that Thanksgiving Day falls on a Wednesday? What is the probability that Thanksgiving Day falls on Thursday? Thanksgiving Day is always on a Thursday. So probability for Thanksgiving Day falls on Wednesday is equal to 0. It's impossible, right? And probability for Thanksgiving Day fall on Thursday is equal to 1, which is always true. So probability of impossible event is 0. So we use P parenthesis now set equal to 0. And probability of certain event is 1. And we use probability of omega equals to 1. Omega represents a certain event. So for any particular event, the probability of that event is between 0 as greater equal than 0 and less than equal than 1. If that AC denotes the complement event to A, then probability of event A plus probability of complement of event A equal to 1. So this is very important. So if X denotes the number of phase, the phase a die could shows when it lands, then probability for X equals 7 will be 0 because the phase will never be 7, right? It's only between 1 and 6. And for probability for X is less or equal than 7 will be always 1, because 1, 2, 3, 4, 5, 6 is all of them are below 7. So probability for X not even equals probability equals to 1 minus probability X. The phase is even, right? So probability for X is greater or equal than 0 is 1. That's a certain event. Every number we can get will be bigger than 0. And probability for event A equals 0 only if A cannot occur. For any event, probability of A is less or equal than 1. If Y denotes the sum of the numbers on the face when throwing 2 dice, so probability for Y equal to 1 is equal to 0. It's impossible, right? No matter what face you're going to get, the minimum you can get is 2. Cannot be 1. So this is an impossible event. Probability for the sum of 2 faces is greater or equal than 2, less than equal than 12. That's equals 1. That's a certain event. No matter what happened, right? Whatever result you get, it's gotta be between 2 and 12. Probability for Y equals 4. The sum of 2 faces equals 4 is 3 out of 36. It could be 1, 3, combination of 1, 3, combination of 2, 2, combination of 3, 1. So probability for the complement event of Y equals 2 will be equals to 1 minus probability of Y equals 2. So which is 1 minus 1 over 36. Probability of getting sum of the 2 faces equals 2 will be just 1 out of 36. So the final answer will be 35 over 36. A compound event is an event combining 2 or more simple events. So let's take a look at some notations. So probability for A intercept B, meaning interception of A and B. Another way of describing this is called both A and B occur. Probability for A union B is basically union of A, even A and B. So that means either A or B or both could occur. So our addition rule states like this, right? So probability of A union B equals probability of A plus probability of B minus probability of A intercept B. And let's use the Venn diagram to describe this particular addition rule. So we get an even A here, we get even B here, and then let's intercept the A and B here. So basically the thing is when we add in even A and probability of even A and probability of even B, we add in an interception twice. That is why we subtract interception once. we don't double counting any parts of the event, right? So that is why we subtract probability of A intercept B. So you get that. This is for overlapping events. If not overlapping events, then probability of A intercept B will be 0. So that's okay, right? So we can just add probability of A and probability of B. Even A and B are disjoint or mutually exclusive if they cannot both occur together. In such a case, the intersection of even A and B is empty. So A intercept B is not set, so which is 0. So probability of A addition rule stated as following: probability of A union B equals probability of A plus probability of B, which is our addition rule. Let's take a look at example of addition rules. So this is a particular table we see in the beginning of the chapter. So this table summarizes the pregnancy test results. So we get a positive test results, negative test results, subject pregnant, subject not pregnant. So this 80 means subject pregnant, but the test result shows positive. And this 11 means subject not pregnant, and the result shows negative. So this 5 means subject pregnant, but the test result shows negative. And here the 3 means subject not pregnant, but test result shows positive. Which one is worse? Subject not pregnant, test result shows positive, or subject pregnant and test result show negative? Think about it. We get clinical trials of pregnancy tests, assuming that one person is selected at random from the 99 people in the test. Find the probability of selecting a subject who is pregnant or had a positive test result. So probability of so here we have to use a addition rule, right? So we have it's a union of pregnant subject and a positive test results. So probability of pregnant equals to 80 plus 5. Total people who is pregnant is this, 80 plus 5, which is 85 by 99. Probability of positive test result equals to 80 plus 3. It's on this particular row, 80 plus 3, which is 83 by 99. And probability of pregnant and test positive, which is the intercept of pregnant and positive test results, which is 80. So it's 80 over 99. So probability of pregnant or test positive equals to probability of pregnant plus probability of test positive minus probability of pregnant and test positive, which is equals to 85 over 99 plus 83 over 99 minus 80 over 99, which is 88 over 99, which is A over 9. And the final result in decimal is 0.899. Alternatively, you can do this, right? Probability of pregnant or positive equals probability of pregnant and positive plus probability of pregnant and negative plus probability of not pregnant but positive. You end up with 80 over 99 plus 5 over 99 plus 3 over 99, which is the same result. So basically you need to subtract to avoid double counting. That's the key thing about addition rule when they are joint event. Multiplication rule. So multiplication rule is basically probability of A and B equals to probability of A intercept B. Example. So we answer the following question at random, meaning you have no knowledge about it. You just pick the answer. So first one is true and false question. So a pound of feathers is heavier than a pound of gold. So you pick answer, whatever it is. The second question is, which has affected society most? A, remote control. B, sneakers with high heels. C, hostess Twinkies. D, computers. E cell phone. So the probability at random, a choice has, for question 1 will be a choice has probability 1.5. So probability of getting correct answer will be half. Getting wrong answer will be half too. So here we want to to answer the random question number 2. Each choice is a probability of 1/5. So probability of getting correct answer is 1/5. Probability of getting wrong answer will be 4/5. So in order to get probability of both answers correct, so which is probability of D, T, and D. For question 1, it is true, and question 2, the answer is D. So probability of getting a true answer in that particular question 1 is half. Probability of getting D in the second question will be 1/5. So you multiply them and get 1/10. We can also construct a tree diagram like this. So this is a typical tree diagram. So this is starting point. Then we go to the first answer choices, get true and false. Move on to next answer choices. We have A, B, C, D, E for both. So that gives us 10 answer choices, and only one combination of them will be correct. So that probability for both answers correct will be 1/10. Next thing, let's take a look at the multiplication rule. So we have in case of independent events. So if events A and B are independent, then probability of A intercept B equals to probability of A times probability of B. So here the independence is very crucial. So occurrence of one event does not affect the other. So that's what independence means. So example, let's first of all take a look at throwing 2 dice. What is the probability that the first number is even and the second number is larger than 4? Are they independent? Yes. And no. Result of first number has no impact on the result of second number. So they are independent. So we want to first die even, second die larger than 4. So probability for first die even is we can get 2, 4, 6. So it's 3 out of 6. So it's half. Probability of a second die larger than 4. So face has to show either 5 or 6. So it's 2/6, which is 1/3. So probability of A intercept B equals probability of A times probability of B, which is equals 1/2 times 1/3, which is 1/6. Alternatively, from the graph, there are 6 options that are good. So look at these. This table lists all the possible outcomes here. So so 6 options are good. So it's 2/5, 2/6, 2/5, 2/6, 4/5, 4/6, 6/5, 6/6. So probability of A intercept B equals 6/36 equals 1/6. That matches with our result of using multiplication rule. So if 2p's multiplication rule without replacement, this is without replacement case. So if 2p's are chosen at random without replacement, what is probability that first one has a green part and the second one has a yellow one? So first selection, take a look at this. Green part will be how many? The counting is 9 out of total 14. So now we have 14 p's. Second selection, so since it's without replacement, that means when you pick a green part, you don't put back in our original setting, so you throw it away. So probability for the second selection to be a yellow part will be, we still have 5 yellow parts here, right? But the total number of P's remaining is 13. So it's 5 over 13. So probability of getting first green part and second yellow part is equals to probability of getting a green part, the first selection, times probability of getting a yellow part, the second selection, which is equals 9 over 14 times 5 over 13, which is, when you convert to decimal, is 0.247. So must take into account is without replacement. So next thing, let's take a look at a conditional probability. So first thing, conditional probability B given A will be means conditional probability of A, B given A. So that means we try to figure out probability of event B occurring given that event A has occurred. So probability of A given B, which is probability of event A occurring given that event B has occurred. So these two notations are completely different. So gotta be careful about this. A general multiplication rule is probability A and B equals probability of A given B times probability of B. Let's take a look at example, right? So CD control damage. So water, crushing, punching, puncture, marking, 5 damage items. So WCC PM, 2 items are selected randomly with replacement probability of first item C, second item C. So it's equals to probability of CC equals 2 over 5 times 2 over 5, which is 4 over 25 equals 0.16. That's with replacement, right? Without replacement, PCC equals to first probability of first C occurring is 2 over 5. Probability of second C occurring is 1 over 4, which is 2 over 20, which is 0.1. Let's look at another multiplication example, right? Probability of 4 aces in forecast. So you suffer a deck of 52 cards, right? You want to get 4 aces in a row. So probability of getting first ace is 4 over, this is a typical multiplication rule without replacement. Probability getting first ace is equals to 4 over 12, 4 over 52. Probability getting second ace is probability is equals to 3 over 51. And probability of getting third ace is equals to 2 over 50. And probability of getting last ace will be 1 over 49. So you multiply all these probability together, you get the answer. Here, remember, it's without replacement when you apply the application rule. And put some homework problem here, so if you get time, you can try this. So next thing, let's move on to at least one event. So at least one here means one or more. So complement event of at least one will be none. None of that happen. So let's say we want a probability of at least one girl among 3 children. That means we want to, that is equals 1 minus probability of at least one girl. The complement event of at least one girl will be no girl. So that means we want all 3 boys, right? That will be boy, boy, boy. And the probability of that occurring will be 1 over 8. So the probability of at least one girl among 3 children will be 1 minus 1 over 8, which is 7 over 8, which is equal to 0.875. So let's go back to conditional probability a little bit more. So the conditional probability of an event A given B is denoted by probability A, vertical line B, and then it is the probability that A occurs, knowing that B has occurred already. So probability of A given B equals the probability of A and B divided by probability of B. And let's look at the example. So here we have a pregnancy test result. So the table lists all the data here, right? So here I add up the row total and the column total. So this 85 means the total amount of subjects which are pregnant, and this 83 means total amount of subjects has positive test result. 14 means total amount of subjects not pregnant. 16 means total amount of people who has test negative. One subject is selected randomly. Find the probability of subject being positive given that she's pregnant. So probability of positive given pregnant equals to positive given pregnancy 80 over 85. Right, so that's for the formula. So probability of positive given that pregnant, no. So the probability for that will be 85 over 99, right? No, that would be 80 over 99. Positive pregnant, that's the intercept of pregnant and test positive, which is 80. So the probability of that occur is 80 over 99. And probability of pregnant will be total amount of subject are pregnant is 85 over 99. So we divide these two probability, we're gonna get 80 over 85, which is approximately 0.964. So let's look at another example about conditional probability. It's about Titanic mortality rate. So we get survived, died, men, women, boy, girls, right? So let's summarize the table. So put it here, I sum out the row total and the column total, and total the subject with survey. So when you encounter the conditional probability involving the table, the first thing you need to do is compute the row total and column totals. And that's a key thing. That's very first thing you need to do. So here this 706 represent the total amount of people who survived, including men, women, boys, girls, right? And this 1692 represent the total amount of men in the Titanic. And 2223 includes all people who is on Titanic. So the conditional probability of man given that died is probability of a man. So we're apply the formula. Probability man and died is 1360, right? 1360 over 2223. Probability of amount of people died is 1517. 1517 over 2223. So probability is equals to 1360 over 1517, which is equals 0.897. And the probability of die given that as a man, these two are totally different, right? So it's equals probability of man who are die, which is 1360 over probability of man. Total amount of man here will be 1692. So you divide and you get 0.804. So probability man die. That means among all those people who died, what proportion of men is that? Probability of a die given man, it's among all those men, proportion of men who died. So let's take a look at some counting rules, right? So first one is called fundamental counting rule. So if event A could occur in m different ways, and event B occurring in m different ways, the events together could occur in a total of m times m ways. Let's look at combination log example, right? Combination log has 3 dials with digits from 9 to 0. So between digits 9 and 0, there are 10 numbers between. So let me show you a quick formula to compute this, which is using 9 minus 0, adding 1. So remember, always adding 1. 9 minus 0, adding 1, equal 10. So total number of digits between 0 and 9 will be 10. So total number of combination will be 10 times 10 times 10, which is 10 raised to 3 power, which is 1,000. And bike lock of with 4 dials from equal digits between 1 to 6. So between 1 and 6 will be 6 digits. So 4 dials will be, we apply the fundamental counting rules, is 6 times 6 times 6 times 6. It's 6 raised to 4th power, which is 1296. Also, this is an interesting example. Arrangement of ABC, right? So you can arrange these 3 letters in 6 different ways. ABC, ACB, BAC, BCA, CAB, and CBA, which is 6 total. Also, take a look at this. If 3 spots, right? Let's say we have 3 ABC, 3 letters, 3 different letters. So our first spot, we have 3 choices, either A or B or C. And because it's rearrangement of this, so we cannot repeat in A. So that's in terms of second spot, there are 2 letters left, either. And when we get to the last spot, it will be 1. So 3 times 2 times 1 give us 6. So that's what we call 3 factorial, basically. 3 times 2 times 1 is 3 factorial. And 4 factorial equals 4 times 3 times 2 times 1. So you always start with this number in terms of factorial. Then you ending at 1. So you multiply all the numbers in between. And 5 factorial is 5 times 4 times 3 times 2 times 1 equals 120. Also, you can take a look at this way, right? 5 factorial basically equals to 5 times 4 factorial. Also, if we divide them, right, we divide 7 factorial by 3 factorial, it's basically equals to 7 times 6 times 5 times 4 times 3 times 2 times 1, dividing by 3 times 2 times 1, and we cancel everything after everything after 3. It's like 3 to 1. You cancel that, so end up with 7 times 6 times 5 times 4. And factorial and permutations. A collection of n different objects could be arranged in n factorial different ways. So in the first spot, there are n possible items to place. So the second one will be n minus 1, third one n minus 2, until the last one will be only 1 choice left. So ways of seating 20 students in class of 20 chairs will be 20 factorials. So 20 factorial is a huge number of answers. Arrangement of 3 letters ABC. We have 3 choices for first spot, second, 2 choices for second, and 1 choice for last. 3 times 2 times 1, which is 6. And ways of seating 4 of the 20 students in 4 pre-assigned chairs. That would be basically for that particular 4 pre-assigned students. For first one will be 20, second one will be 19, 18 times 17, which is, this is basically equals to 20 factorial by 16 factorial. You can basically view this as this. So first of all, seeing 20 students in 20 seats, and then you're sitting the other 16 students in 16 seats. Then those 4 students will be sitting on the 4 pre-assigned chairs. So that's basically consists of a permutation. So it's P24. So the answer is 116,280. So in general, MPK, right? Permutation or picking K object from N object, and then the rearrangement of those K objects matters equals to N factorial by dividing by N minus K parentheses factorial, which is equals to N times N minus 1 times N minus 2, etc. until N times N minus K plus 1. MPK is called a permutation of K objects out of N total objects. So let's look at the formal definition of permutation and combinations. Permutation rules. Basically, all items are different. All the does count. So we're selecting K items from N available items without replacement, and all that matters is MPK. So equals N factorial dividing by N minus K factorial. And combination here, order does not matter. So number of combinations, K items selected from N different items without replacement is NCK, which equals N factorial divided by K factorial times N minus K factorial. Let's take a look at example. The board of trustee of a college has 9 members. Each year, a 3-person committee is chosen. At the same time, the board elects 3 officers, president, VP, and then secretary. How many slots of candidates for officers are possible? Here, we pick 3 persons from out of 9 members, right? 3 officers out of 9 members. And then those 3 officers, they all matters. What? President, VP, secretary has different ranks, so definitely 3 officers order matters. So here, when the order does count for board, it matters who is president, VP, and secretary. Therefore, the permutation of K equals 3 people out of N equals 9 different people equals 9P3. So it's 9 factorial dividing by 9 minus 3 parentheses factorial is 9 factorial by 6 factorial is 9 times 8 times 7. Which is equals to 504. And B, how many different 3-person committees can be chosen? So here order does not count for committee, therefore combinations of K equals 3 people out of N equals 9 different people. So we're using combination to do this, so 9C3 equals 9 factorial by 3 factorial times 9 minus 3 factorial. So it's equals 9 factorial divided by 3 factorial divided by 6 factorial, which is 84.